Okay, so thanks everyone. So with this talk, we would like to show you how we can use stratigraphy of the Somali rifted margin to constrain Afar plume dynamics and understand its relation with opening of the East African rift. Our study area is the area that you can see approximately on this NASA image towards the right. So that is the Somali Basin and Northeastern Africa. For those of you who are not familiar with this study area, I'll first go over the main tectonic features. In the north, our study area is bounded by the Gulf of Aden and Red Sea, which are both young oceanic basins. And the Afar region over here forms the northernmost part of the East African rift. Together with the Ethiopian rift, this Afar region crosses the basalt plateau. And south of the basalt plateau, the East African rift branches into a western and eastern branch that encircle the Tanzanian craton. Offshore, we find the Somali Basin. The Somali Basin formed after rifting and continental breakup, after which Madagascar moved in a southward direction. So that means that this margin here of Eastern Africa is a rifted margin. The eastern side of our study area is this active seafloor spreading ridge. And then within the Somali Basin is a dead spreading ridge. This figure, the map towards the right, shows the location in the red circle, where many studies think that the Afar mantle plume has impinged upon the northeastern African lithosphere. And you can see its relation with the location of the Somali Basin. So in this talk, we will try to answer the following questions. When did the Afar mantle plume impinge upon the northeast African lithosphere, and how is it then related to rifting? And we'll try to answer these questions by looking at dynamic topography caused by a mantle plume. When a mantle plume moves up in the mantle, this upward flow of the mantle plume results in a dynamic swell of the Earth's surface. These dynamic swells can be large, and they basically indicate when the mantle plume reached the upper mantle. So what we're going to do in this talk is look for this dynamic swell or evidence for it in the Somali Basin. So we're going to look at dynamic topography of the Somali Basin. The map that you see towards the left is a map of northeastern Africa, and it shows in the red dot Eocene, so rather old volcanism in northeastern Africa. That red dot is actually located within this Afar plume location impingement zone. So question is whether this Eocene volcanism is associated with the Afar plume or not. And in the grayish areas on the map towards the left, you can see Oligocene to more recent volcanism. So when we look at the topography or elevation of Eastern Africa, we see that it is at an elevation that is higher than you would normally expect. Normally, cratons on Earth are on average about 400 to 500 meters above sea level, and Eastern Africa is at least 500 meters higher than that. This was first recognized by Nyblade and Robinson, who called this the African superswell. Such dynamic or residual topography of the Earth's surface we can calculate, and it's basically the following. Residual topography or dynamic topography of Earth's surface is the elevation of the land surface minus the isostatic elevation, and isostatic elevation is the result of density changes or thickness changes as a result of tectonics, for example, or magmatism. So this map here shows residual topography of the African plate. And as you can see from the scale, this residual topography of Eastern Africa today varies between about 450 and 1,000 meters. Such residual topography or dynamic topography is caused by mantle flow. Upward mantle flow would result in uplift of Earth's surface, so a dynamic swell, and downgoing mantle flow would result in a dynamic depression of Earth's surface. Below Eastern Africa, in the mantle, we find a large low velocity zone. And this large low velocity zone is shown in the image towards the right by the orange color, and this is basically an isosurface. The composition and origin of this large low velocity zone is not known, but several studies agree that this is probably a buoyant structure. And if this buoyant structure in the mantle if this structure in the mantle is indeed buoyant, this would mean it would be moving up to shallower depths and therefore could cause the dynamic topography or the dynamic swell in Eastern Africa. The Afar mantle plume is thought to be a northward continuation of this dynamic swell. So in this talk, we're going to answer the following questions. What are dimensions and timescales of dynamic topography of the Afar plume? And how does this relate to opening of the East African Rift? So for that, we need to focus on the Somali Basin that you can see here in the black box. The Somali Basin formed after rifting and continental breakup, which occurred probably around 165 million years ago. And seafloor spreading ended around 120 million years ago. So this means that the Somali Basin has been tectonically quiet for a very long period of time, which is important for the remainder of our talk. The map towards the left shows the Somali Basin in more detail. You can see there the coastline of Eastern Africa and northern Madagascar. And the pinkish colored area is the area that is close to the Afar mantle plume. So the area that was probably affected by the Afar mantle plume. On the map, you can see also green circles and orange squares, and they indicate DSDP and ODP wells in our study area. The green circles are closer to Afar and the orange squares are further away. Furthermore, on the map, you can see these orange lines and the white line, and they indicate the location of a legacy to the seismic reflection of the Somali coast, the Somali margin, which was first interpreted by Coffin and Rabinowitz. And one of those lines indicated in white is shown here below. So that's one of the seismic reflection lines with the coastal area towards the left. You can see there the well path of the SDP 241 that we used for a well tie. Well, we have interpreted on this line several horizons. In the first place, starting from the bottom, the blue reflector indicates the top of oceanic crust, which is heavily faulted. Then I'm going to move on to the green reflector. This green reflector was first identified in DSDP 241, and it marks an Eocene-Oligocene unconformity. This is actually a hiatus that marks an important transition in lithology. And this transition is from non-calcareous deposition below the hiatus to calcareous deposition above the hiatus. This hiatus is mostly conformable, and we can trace it as a reflector through most of these seismic reflection lines. In some locations, it's non-conformable, and you can see that towards the left of this line, for example. Now, finally, on this line, you can see this red reflector, which is a late Miocene erosional event. This is not related at all to this study, but it shows very nicely an incised channel. Okay, moving on. Towards the right here, you can see a simplified stratigraphic column of DSDP 241. So that is one of the wells that is close to the Afar region. And the green arrow points towards this Eocene-Oligocene unconformity that we just saw on the seismic data. This unconformity or hiatus marks this important dramatic stratigraphic change. Below it, we have no calcareous nanofossils, and above it, we have strata rich in calcareous nanofossils. This remarkable change in lithology we also find in the other wells close to the Afar plume, for example, well DSDP 234. And this is the basis of our analysis. So we're using this change in lithology to mark dynamic uplift of the ocean floor. And we do that making use of the carbonate compensation depth, or CCD, in the ocean basins. Dynamic uplift of the seafloor as a result of the Afar plume may move the seafloor up to above this carbonate compensation depth in the ocean basins. Such carbonate compensation depth, or CCD crossings, can be recognized in marine stratigraphy. So they mark changes in lithology. We can then compare the carbonate states of the wells on and off the dynamic swell related to the Afar plume and calculate amplitude, dimension, and temporal evolution of the dynamic swell. So we use this to pinpoint the arrival of the Afar plume. For those of you who are not familiar with the carbonate compensation depth, I wrote down the definition below. So the carbonate compensation depth, or CCD, is defined as the ocean depth at which carbonate sinking from the photic zone is approximately balanced by this solution so that carbonate accumulation rates approach zero. Now, what does this all mean in practice? It means the following. Towards the left, you can see a typical ocean crust subsidence curve, which on the vertical axis depth and on the horizontal axis time. Also indicated here with this dashed line is the carbonate compensation depth or CCD curve. As the oceanic crust ages, it sinks. And at one point in time, it may sink below the carbonate compensation depth. When that happens, we see this remarkable change in lithology in our wells, from calcareous deposition below to non-calcareous deposition above, after which the seafloor sank below the CCD. Now, a dynamic swell would do the following with our ocean floor. A dynamic swell related to the Afar plume, for example, may lift our ocean floor up above the CCD, resulting in different calcareous and non-calcareous patterns in our well. So you see that example towards the right. When the ocean floor is at shallow depth, there may be a calcareous deposition. At one point in time, the ocean floor may sink below the CCD, resulting in non-calcareous deposition. The dynamic swell may temporarily lift up the ocean floor above the CCD and result again in calcareous deposition. Now, there's one complication to this story, and that is that the CCD varies from place to place in the ocean basins, but also over time. So that means that we calculated the Paleo-CCD for our study area, so the Somali basin, so we could compare our oceanic crust subsidence curves with this CCD that varied over time in our ocean basin. So that is what we do. So our first next step is calculating this ocean crust subsidence curves for all the wells in our study area. And we do that taking the following components, We do that taking the following components into consideration. You see here schematically shown an oceanic crust, which forms at the mid-ocean spreading ridge towards the right. And as the oceanic crust ages, it cools down, resulting in thermal subsidence. So we included that in our Paleo-bathymetry calculations. On the oceanic crust, as it ages, marine sediments are being deposited. They act as a load and isostatically move the ocean crust down, while at the same time, the seafloor package moves the oceanic floor up. So we took both these components into consideration as well. The last component that you can take into consideration are eustatic sea level changes. That gave us all our components to calculate Paleo-bathymetry of our Somali basin. And you can see the components here, and here they are all added up. Now you can see here the Paleo-bathymetry curve for DSTP 241. As you can see, throughout most of its evolution, the seafloor has been below 4 kilometers depth. So a dynamic swell would never lift up this ocean floor above sea level, but again, it may lift it up above the carbonate compensation depth. So I'll show you now the results. First of the 4 wells that are far away from the Afar plume. So you can see the wells here and their typical ocean crust subsidence curves that we calculated for each of them. The open circles that you see here in the many different colors and shapes and sizes indicate the carbonate states of the wells. And the purple line is this paleo carbonate compensation depth that we calculated for the Western Indian Ocean. So these 4 wells that are far away from the plume, they do not show a lift up of the ocean floor above the carbonate compensation depth at the arrival time of the Afar plume. But this story is different for the wells that are close to the Afar plume. You can see 2 examples here, DSTP 241 and DSTP 234. The purple line again is our calculated Paleo-CCD. Now, by comparing and contrasting these lines with each other, we can calculate the most likely elevation of the seafloor that it experienced as a result of this Afar plume. And by comparing the timings of the crossings of these lines, we find age constraints. So we find the following. We find that about 650 meters of uplift occurred about 1,200 kilometers away from the Afar plume center in the westernmost portion of the Somali basin. And this uplift must have begun just a few years prior to 25 million years ago. So this pinpoints the arrival time of the Afar plume. Now, we're going to take this information and now look at the East African Rift and its opening and volcanic history. And I've shown here on this map just some volcanism ages and some rift opening ages. In the beginning of this talk, I mentioned this Eocene 45 million year old volcanism. And also there's a portion of the rift that started opening 45 million years ago. We think that this cannot be related to the Afar plume. It is much too early. However, if you look at the northern portion of the rift zone, we have volcanism dated at about 30 million years ago, and we have poorly constrained uplift estimated between about 30 and 20 million years ago. These are ages that are very close to our age or estimate of Afar plume arrival. So we think that they are closely related. Much later onsets of rifting and volcanism seem difficult to relate to the Afar mantle plume arrival around 25 million years ago. And that is all that I had for you today. So thank you very much.
Thank you, Jolante. Do you have any questions? I would start with one. How do you reconcile the 30 million years ago lava ages in Afar and the uplift? Does it mean that the uplift occurred after the volcanism?
No. So in this short talk, of course, I didn't have time to talk about the entire dynamic swell. So with this, we can constrain rather well this dynamic uplift start in the Somali basin, but you can imagine that it started a few million years earlier in the Afar region itself. We just don't think that you could say that it had started 45 million years ago in the Afar region. That is too much of an age gap. So that's a really good point. So yes, the 30 million year old uplift, estimated uplift, and start of volcanism there, I think fits our story really well.
So you would say that it took the front of the impinged plume head 5 million years to go from Afar to the Somali margin?
Yeah, maybe a few million years before it had affected that area. Yeah, that's a good point. Good question.
Okay, thank you. Gary, next question.
It's a nice talk, Jolante. I like the hypothesis. But, and I may have missed this, you may have said it, I was answering other questions. But if I uplift the offshore area by, say, 1 kilometer or 650 meters, then the coastline and onshore regions of the Somali region should have formed significant topography. And I would imagine has been incised and eroded rather significantly in the Oligocene. Is there observation of such marginal working?
We are looking into that for our paper. So we haven't found clear evidence of that. So there, what you would expect is a change of the coastline. And so it is actually something that we're looking into. So we haven't found documentation of it, but we're very aware of this being another constraint. it's an excellent point. Thank you.
Thank you.
Jolante, you were really well in time. That's why we have even time for another question. Bernhard, please. Bernhard,
yeah, can you hear me now?
Yes.
Yeah, it essentially has been already addressed by the previous question. So it was just whether this time delay, 5 million years between the plumes and plume impingement and the uplift, that's dynamically reasonable with the velocities you would expect for plume material.
Yeah, I think this is reasonable. So there are studies of Mucha and other people who have calculated paleodynamic topography of this region. And when we compared our predictions with their geodynamics-based, geodynamic modeling-based predictions, they compare rather well. The cool thing about this is this gives us a pinpoint, right? This gives us really an age and a dimension. So you could also go back and assuming that this is a data point or an observation that is correct, if we could learn something else about plume dynamics, for example, or velocities or changes that you would expect in dynamic swells.
Okay, thank you.
Thank you very much, Jolante. We move on to the next speaker.